Welcome to the second video in this series on thermodynamics and chemistry. In the previous video, linked in the description below, we looked at the definitions of thermodynamics as to what a system is and what the direction of heat and energy flow are. We also looked in some detail about how work is treated in thermodynamic systems. In this video, we'll go into more detail on heat because the flow of energy is essential for a chemical reaction. The flow of energy in nature is well established. Everyone knows that energy flows spontaneously from high to low. Therefore, as heat and energy are both measured in joules, dQ, the heat flow, or the change in heat, is measured as a change, which is always final minus initial. So, since the final state in a spontaneous process is always lower than the initial state, dQ is going to be the heat of the final state at a low energy minus the heat of the initial state at a high energy. Put simply, but very importantly, when heat flow is negative, that is said to be exothermic for a specific process. And that is the spontaneous direction for that process to go in. Heat flow can be quantified and measured through a process or a technique called calorimetry. Like any other analytical technique, in calorimetry, one is comparing a known to an unknown. The known is what's called the calorimeter, and the unknown is the reaction or the process taking place in this device called a calorimeter. A calorimeter is essentially a container, and it can come in two types. You can have a constant volume calorimeter, where mass, it's a closed system, mass cannot get in or out, so pressure changes. Or you can have a constant pressure calorimeter, where volume can get in and out, and pressure stays the same. Essentially, once again, a coffee cup. The important thing that a calorimeter must have going for it is that it must be adiabatic, meaning heat cannot flow in or out of the calorimeter. This makes quantifying things easier since heat can't escape. That simply means that however much heat the reaction loses, the calorimeter gains, or if the reaction is gaining heat, the calorimeter is losing it. dQ of the reaction is always going to be equal but opposite to the change in heat of the calorimeter. Using this as an example, I dissolve a salt. 1 gram of ammonium nitrate is placed in a constant pressure calorimeter, essentially a styrofoam cup, containing 50 grams of water, which is a known. It has a known specific heat of 4.18 joules per gram degree Celsius. The water is initially at 25 degrees C. The calorimeter is at 25 degrees C. After the salt dissolves, the water temperature drops to 23.3 degrees C. What is the heat of solution for dissolving ammonium nitrate? One starts with the fact that the heat of the reaction is equal to minus the heat of the calorimeter. And the calorimeter in this case is the known, is the water. The definition of heat, as seen from the previous video, linked in the description below, is mass times specific heat times the change in temperature. All of these are known for the water. They are not known for the reaction. So the heat of the reaction is going to be equal to minus 50 grams of water times 4.18 joules per gram degree Celsius times the difference of 23.3 and final minus initial, 23.3 minus 25 degrees C. And again, watching one's units, the grams are going to cancel, Celsius cancels, and one is left with this reaction having a heat of plus 351 joules. The plus, again, is tells you which direction it goes in. In this case, energy has to be added to the reaction for it to go forward. This shouldn't be surprising since the ammonium ion is positive and the nitrate is negative. That's a very, very strong attraction. And much like separating magnets, separating pluses and minuses is possible, but you have to put in energy. In this case, the water adds 351 joules of energy to separate the charges. This heat flow is actually, however, an extrinsic property, meaning it's how many joules it takes to dissolve 1 gram of the salt. An extrinsic or extensive property is generally not useful because it depends upon how much material you have. In chemistry and the physical sciences, things are created into intrinsic properties. In this case, heat flow intrinsically is called enthalpy, symbolized by the letter H. It's intrinsic because it is normalized to 1 mole. Heat is measured in joules, enthalpy is joules per mole. So in our reaction, if it takes 351 joules has to be added to dissolve 1 gram of ammonium nitrate, and ammonium nitrate weighs 80 grams per mole, again multiplying, grams cancel, and I now have a heat of this reaction, a delta H, of 28,090 joules per mole. This heat of reaction can be now used as part of the balanced equation, as can be seen by the following. It turns out anything with a delta in front of it is what's called a state function. Once again, it measures the change, final minus initial. Importantly, this is irregardless of the path taken. As long as you start in the same place and end in the same place, the change in potential remains the same. Much like taking the stairs or the elevator, you might do more work taking the stairs, however, you're starting and ending in the same place in the building. The importance of this can be seen by something called Hess's law. And Hess's law is best shown by an example. I have something I do not know. A reaction of 3 carbons and 4 hydrogens to make C3H8. I do not know what the energy of that reaction is, what the heat of the reaction is, but I do know several other things. I know how to make carbon dioxide. Carbon plus O2 makes CO2 with a delta H of minus 393.5 kilojoules per mole. I know how to make water. 2 hydrogens plus oxygen make 2 waters and also releases 483.6 kilojoules per mole exothermically. Energy is released. Also, C3H8 is propane. It's a fuel. It can burn. C3H8 and 5 oxygens will burn to give 3 carbon dioxides and 4 moles of water, and will also release 243 kilojoules per mole. Hess's law is essentially a puzzle. Make a pathway out of these 3 knowns to give you the original reaction. How this is done is simply by reading from left to right. The first thing I'm looking for is carbon. I see carbon in the first reaction. I want carbon on the right-hand side of the reaction. It already is on the right-hand side of the reaction. However, I need 3 moles of carbon. I only have 1. So, multiplying the balanced equation by 3 to 3 carbons and 3 oxygens get 3 CO2s also triples the energy. If 1 mole takes minus 393.5 kilojoules to make, 3 moles of CO2 takes 3 times as much, minus 1180.5. Moving along left to right, the next compound you need is hydrogen. Once again, you find that alone in reactant number 2. It's on the right side, which is where you want it. However, I need 4 hydrogens, but I only have 2. Therefore, the second reaction has to be multiplied by 2, where 4 hydrogens and 2 oxygens to make 4 waters will give me twice as much heat, minus 967.2 kilojoules. Finally, all to the way to the right, I am looking for C3H8. I find that in the third reaction. I need 1 C3H8. I have 1 C3H8. However, this time, I am looking for C3H8 on the right, but I have it on the left. If I reverse this reaction, 3 CO2 and 4 waters goes to C3H8 and 5 oxygens. Delta, again, is always final minus initial. So if one turns the reaction around, final and initial swap, essentially the only thing that happens is the sign changes. If going forward, the reaction releases 2,043 kilojoules, reversing the reaction would mean you'd have to add 2,043 kilojoules. Once one has the pathway established, double checks one's answer, add up the reactions. Whatever's showing up on opposite sides of the arrows is going to cancel. So I have 3 CO2s on either side, 4 waters on the right and the left. Oxygen, I have 5 on the right and 3 plus 2 on the left cancel. I'm left with 3 carbon, 4 hydrogen, goes to C3H8. That is the reaction that I'm looking for. So Hess's law says if you can add up the steps, you can add up the heats. So once you establish the path, adding up the heats would give the heat of this reaction, this previously unknown reaction, as being minus 104.7 kilojoules per mole, or again, exothermic and hence spontaneous, going downhill. This is important. Hess's law is useful if one looks closely at one of these reactions. You note C plus O2 goes to CO2 at minus 393.5 kilojoules per mole. In this reaction, carbon's a solid, oxygen's a gas, CO2's a gas. What you are looking at is the heat required to make 1 mole of a compound, in this case CO2, directly from the elements in their native states under standard conditions. So in this case, the native state of carbon is C as a solid. Oxygen under standard conditions exists as a gas and a dimer O2. This type of enthalpy is called a heat of formation. What makes heat of formations useful is that they are tabulated. In the back of every single book, you will find a series of heats of formation. Therefore, for any given reaction, A plus B goes to C plus D. If I want to know the delta H, the heat of that reaction, delta is always final minus initial. In the case of a chemical reaction, final minus initial, your final state is products, your initial state is reactants. So delta H of a reaction, final minus initial, is going to be very simply the sum of the heat of formation of all the products minus the sums of all the heats of formation of the reactants. One can see that this is a very powerful way of looking at any given chemical reaction. You do not have to know or perform the reaction rather in order to know the outcome. So, If I have methane, CH4, and 2 oxygens going to CO2 and 2 moles of liquid water, using a table, I can predict what's going to happen in this reaction. My products, the heat of formation of CO2 and the heat of formation of water, minus my reactants, methane plus oxygen, as related by the balanced equation. I have 1 CO2, but since I have 2 moles of water, that's going to have double the heat, 2 times the heat of formation of water. On the other side, I have 1 CH4, but I have 2 moles of oxygen, so it will double the heat of formation of oxygen. At this time, as mentioned, all of these values are known and tabulated. Very simply, looking it up, it's going to be minus 393.5 kilojoules for CO2, 2 times minus 241.8 kilojoules for water, plus 74.6 kilojoules per mole for CH4. And oxygen as an element has no heat of formation, 0, because it takes no energy to make oxygen out of oxygen. Adding up these known energies gives you an answer, first of all, minus 802.5 kilojoules. More importantly, to indicate how powerful and useful this is in the real world, I've added up the energies and got a negative sign, meaning this reaction is spontaneous. It is exothermic. Therefore, without performing the reaction, I was able to determine that this reaction will go forward in the real world. So, heat flow is important in chemistry because everything in nature moves spontaneously from high to low. If one knows the energies of the reactants and the products, one can determine a priori which way the reaction will move. In the next video in this series, linked in the description below, we'll go into more detail and find out that heat flow alone, however, does not determine whether a process moves forward. Thank you very much for listening, and I hope you found this video useful.